All right, thank you very much for the organizers for organizing and having me speak here. I am going to talk about yet another application of Shlyakhtenko's. Let me write A values. Here. Semicircular system construction. So before I tell you what this construction is really about, I want to remind you that this is, Shlyakhtenko's A value semicircular system construction is a generalization of Voiculescu's free Gaussian functor, which is in turn a generalization of the Gaussian functor. And so the Gaussian functor, the reason why we're saying it's a functor is that when we have a representation, let's say orthogonal representation of a group, G, when we use the Gaussian functor, this will give us a G action measure preserving on a probability space. And then, so for Shlyakhtenko's A value semicircular construction, you start with a symmetric bimodule of a von Neumann algebra. I'll only consider tracure once. Then you get a larger trivial von Neumann algebra. Let's call it phi of AH. I'll be more explicit about how these constructions go. And then, okay. So in this talk, I'll be going back and forth between groups and two-one factors, and group representations and bimodules. And then also actions and inclusions, because those are the correct analog. Okay, so, okay. The application, the main one that I wanted to talk about is about, it's safe to say, spectral gap characterization of property T. And the reason why I wanted to put the Gaussian functor here is I want to make a comparison of both spectral gap characterizations of property T for groups and for two-one factors. And both the statements and the proof align really well. So one using Shlyakhtenko's A value semicircular construction and one using the Gaussian functor. Okay, maybe I. So Jesse already mentioned the definition of property T. I'm just gonna briefly repeat it. Okay, so I am only going to consider countable groups and two-one factors are separable. Countable. G has property T if every unitary representation pi of G on H with almost invariant vectors has non-zero invariant vectors. And this was by Kashan, 67. And then the corresponding notion for 2-on factor let's call it A, has property T if for every A bimodule with almost acentral vectors has non-zero acentral vectors. And this was formulated by Kohn in 1980. And Jesse also mentioned that there are relative versions for both groups and von Neumann algebras. So this was done for 2-on factors, and then later, more generally for trivial von Neumann algebras by Kohn and Weiss in '83. A relative version by Margulis and Popa. Right, so examples as in Z when n is greater than 3, and example here, the group vector of any property T groups. Okay, so maybe I write G has property T, only a group von Neumann algebra has property T. Okay. So, spectral gap characterization of property T. So property T is regarded as an important rigidity notion that has become really basic in a lot of subjects. And spectral gap is also a rigidity property weaker than property T. And therefore, we want to use as if this characterizes property T. So on the group side, we have the following. So this is result by multiple groups of people. Weiss, 1980. Becker, Bolat, 1993. Okay, so what does this theorem say? It's basically saying what I am using I'm only considering countable groups, but so they actually prove it for locally compact groups. So for a countable group G, the following are equivalent. So 1, G has property T. Oh. And then 2, so I should already say that this is a dynamical characterization of property T for groups. And 2, every ergodic PMP action of G is strongly ergodic. And then 3, every weakly mixing PMP action of G is strongly ergodic. Okay, so I will go over all of these properties, what do they mean, in just a moment. But before that, let me write down the corresponding statement for 2n factors. And you see that they are completely aligned. So for a 2n factor, let me call it A, the following are equivalent. So 1 is that A has property T, and then 2, every inclusion of A into a trivial von Neumann algebra, let's say M, has weak spectral gap. And then 3, every weakly mixing inclusion of A into a trivial von Neumann algebra M has weak spectral gap. Okay, so you see, here, if you want the statements to be completely aligned, I guess I should include irreducible. Okay, right, so as I said, they're completely aligned. So the ergodic action, PMP action of a group should correspond to irreducible inclusion. And then weakly mixing action corresponds to weakly mixing inclusion. And strongly ergodic is really a spectral gap property. Okay, let me make them explicit. Right. So for group, for a group action G on, sorry, let me put BMP action. So you have a probability space, omega, and G is acting measure preservingly. And this is said to be ergodic if every G invariant subset of omega is null or conal. So ergodic if E inside omega is G invariant, then it has measure 1 or 0. So you can easily get a representation from action. And this is equivalent to say that the corresponding representation of G on L2 has no non-trivial invariant vectors. And strongly ergodic is really saying that it has no non-trivial, almost invariant subsets. So if you have, okay, so if there does not exist ENs inside omega with symmetric difference of ENs being acted by any group, elements goes to 0, And En is not asymptotically null or conull. Okay. So this can be implied by the corresponding representation of G on the subspace of L2 of omega orthogonal to the constants. Has no almost invariant vectors. Okay. So you see, this tells you this is a spectral gap property. And then weakly mixing. This action is weakly mixing if, when you look at the diagonal, action of G into the product space, omega times omega. This is ergodic. So when you notice that the corresponding representation is just the tensor of the original representation, this tells you that it's the same as saying that this tensor has no invariant vector. Or you might know that this just means that the original representation has no non-zero finite dimensional subrepresentation. And that is the definition of weak mixingness for a representation. Okay, so on the von Neumann algebra side, irreducible inclusion. So this inclusion is irreducible if the relative commutant of A inside the larger traditional von Neumann algebra is trivial. So that means when you cut down the part that actually commutes with A, which is just trivial constants corresponding to thing here, you don't have anything that commutes with A. And has weak spectral gap. So this is the notion by Popa 09. So it's easy to say that this actually gives you a representation of A into L2 of M, and you can make sense of what does it mean for this representation to have spectral gap. And then weak spectral gap is just, instead of considering the vectors in L2 of M, you consider the bounded vectors actually inside M, or just the unit ball of M. So if every vector inside, sequence of vector inside unit ball of M with, that is, okay. So they are asymptotically commuting with A, then they have to asymptotically live in the part that actually commutes with A. So that means so this conditional expectation you can just think of as projecting this vector onto the space of A central vectors inside M. So if you exclude that part, you don't have, you have vanishing vectors. Okay, and weakly mixing inclusion, this just means that when you look at L2 of M, when you take out L2 of A, what's left is still an A bimodule because it's invariant under A. This bimodule is weakly mixing. So weak mixing bimodules notion introduced by Peterson, Sinclair, 09. So if you want, this just means that when you do the bimodule tensor of H with itself, okay, I'm taking symmetric bimodule, but if you're not, you do the conjugate, has no acentral vectors. And equivalently, this has this bimodule does not have finite dimensional A subbimodule. Okay, so I'm not thinking about left or right. I'm just taking, so this can be deal with when you just symmetrize your bimodule. So that's not an issue. Okay, so after decoding all of these terms, you can see that one direction is relatively easy, right? So if you go from having property T, then you look at the, just take any ergodic PMP action, or even weakly mixing action. So this tells you that the corresponding representation on the L2 subspace of the functions that is orthogonal to the constants have no invariant vectors. So no invariant vectors meaning no almost invariant vectors. And no almost invariant vectors is just strongly ergodic. Okay, so before you even know anything about these functors, that tells you you can go backwards. You already have this one direction. And same for 2-1 factor A. If you have A has property T, then an inclusion of A into M gives you the bimodule L2 of M. Sorry, A bimodule L2 of M. And then when you look at this bimodule, you see that once you take out the part that's commuting with A, you don't have things almost commuting with A. So this tells you that's weak spectral gap. And so with the functors, that would do the trick of going backwards. Okay. Okay, maybe I want to say one more thing. So Schmidt did 1 implies 2. And then Kohn and Weiss, 2 implies 1. And then Becker and Valette, 3. So everything related to 3. Okay, so of course you don't need the direction that going to 3, it's just how to go from 3 to other ones. Okay. All right, so I'm just going to briefly tell you how this Gaussian functor gives you the backward, yes. Oh, sorry, I thought, okay. Backward direction, and then Shlyakhtenko's construction gives you these directions. Okay, so for groups, if G does not have T, so now we're doing backwards, right? So you can assume that G does not have property T, then you want to cook up some weakly mixing PMP action that is actually not strongly ergodic. So G does not have T, then there exists some weakly mixing representation. So this is actually the part where Becker-Valette is involved. Okay. Weakly mixing representation with almost invariant vectors. So they, from their proof, you can see that this, you can just actually take the representation to be the complexified representation of some orthogonal representation, which I still denote as pi and h, because so the Gaussian functor require you to have orthogonal representation. Okay, so you go from this representation to the symmetric Fock space, and then complexified the symmetric Fock space. You go from this Hilbert space, so this is part where you're working with this Gaussian functor. So let me call it K, Gaussian Hilbert space. And then with the Gaussian functor, you get L2 of a probability space, which is isometric to the symmetric Fock space, and also intertwines your representation. Maybe I write, so G. Okay, so, and then you complexify it. So the good thing here is that whenever you started with a weakly mixing representation, you would get that inside the symmetric Fock space, when you take out the constant part, you get that the representation of G inside that part is still weakly mixing. So I would just write, so the symmetric Fock space minus the constant part is just the direct sum of all of the symmetric n-tensors of H, and then natural action of G on every tensor. And then So this, and when you go from this symmetric Fock space to here, right? Remember, you have this action of G on this space. So this would, in turn, imply this action is weakly mixing. Okay. And then we also wanted that this action is not strongly ergodic, right? So, so this would be coming from this part because you started with representation with almost invariant vector. So you trace the arrows, you would see that when you go from almost invariant vectors here, and then all the way down here, and then down here, down here, the corresponding set of elements inside here with this, where the values of this Gaussian random variable, that being the image of the almost invariant vectors, is positive, will give you the almost invariant set. Okay. I'm just going to write not strongly ergodic. Okay, sorry. Okay, I should get to the two-one factor part. Okay. So for two-one factor A, it does not have property T. And there exists a weak mixing bimodule of A. So this part is the Beckett-Valette analog for property T two-one factors, which you will have to work on. Sorry, has already been worked on, but it's not, it's not obvious. So weak mixing with almost acentral vectors. Again, called psi n. Okay, so going from bimodules to an inclusion, the larger tracial von Neumann algebras, we use Shlyakhtenko's A-value semicircular construction. So this construction, you start with, you don't necessarily have to start with a tracial von Neumann algebra in Demos' original construction, but that's what matters to me because I'm looking at two-one factors. And then the input also include a symmetric bimodule A, but that's not a problem because for every A bimodule, you can symmetrize A by just doing a direct sum with the conjugate. And then the almost invariant vectors remain. Okay, so a symmetric, let me just write. Okay, and then full Fock space. So Yoon, in her talk on Tuesday, described the construction using covariance matrix, but it's really the same because the bimodules corresponds to completely positive maps. And okay, so full Fock space, given the symmetric bimodule H, is just direct sum in the place where you have constants, you put L2 of A, and then direct sum all of the n-fold tensor product of H. And remember, this tensor is the confusion tensor or bimodule tensor, which arise from the inner product, the A inner product of H. Okay. So vacuum vector here is just the unit of A inside this thing. And then we also have creation operator and annihilation operator. And we are just going to take okay. Going to take a bounded vector inside the bimodule, and so how is it going to act on this full Fock space? If you take a vector here to H and then shift all of the tensors in the most natural way. Okay, and then the semicircular system is all of the, you take this creation operator, you symmetrize it, and look at all of the vectors, bounded vectors inside your original bimodule. This is your semicircular family. Okay. All right, and then the things that we're after, this larger trace over Norman algebra is going to be generated by A, which you started with, and the semicircular family. Right, and you notice that this is actually trivial with the state given by the vacuum vector. And one last thing I want to point out is that when you look at, okay, we are going to start calling this thing M, because this is the M that I wanted. That's going to be, okay. L2 of M is, yeah, the same as the full Fock space as A bimodules. Right, I forgot to mention that you have a very natural action of A here, so it's an A bimodule. All right, so we've done that. Let me tell you how this goes very briefly. Right, so if you start with a not having property T, right, and then you have a weakly mixing A bimodule with almost acentral vectors psi n. Okay, what does it mean for the bimodule to be weakly mixing? This simply tells you that you don't have acentral vectors here, right? So when you cut down the part, you get a weakly mixing bimodule of L2 of M minus L2 of A without acentral vectors. So this is really saying that, right, the definition here, the inclusion is weakly mixing. Okay, and then the almost acentral vectors psi n. So what you do is you, So what you do is you look at S of psi n. Then, if they are almost acentral, well, of course, you wanted to do some manipulation to make them bounded, and then they will stay almost acentral inside phi of AH. Okay, so M, right? And this gives the not weak spectral gap of the inclusion. I will stop there, sorry.